Jnanam paramam dheyam. Knowledge is supreme.
So now we begin the second part of our discussion, concluding remarks 2 for two-level system. This is where we got that you must have a population inversion. Population of the higher level must be more than the population of the lower level in order for you to have gain, in order for you to have more number of photons to come out of the system than the number of photons that you put in. And this has direct relevance to something that is now very, very familiar to us anyway, lasers. I think you told me in one of the earlier classes what is the meaning of laser? Light amplification by stimulated emission of radiation, right? So if I have to have light amplification by stimulated emission, then my gain must be more, right? I should not have a loss. So let us see if that is going to happen. Do I have population inversion in a two-level system? That's what we want to know. In order to answer the question, what we do is we write once again a rate law kind of expression. Okay? Let us write the expression for dNm dt. What is Nm? Population of the higher level. That is equal to what? It gets populated by absorption, right? So the first term I can write is B rho nu NL. Okay? And it gets depopulated by, first of all, stimulated emission and then your spontaneous emission, right? Let me write the terms for that. For stimulated emission, the term is minus B rho nu Nm minus A Nm. Any question about this? Do you understand why B is multiplied by rho but A is not? Why have I not multiplied the last term by rho? It's spontaneous emission, right? Even if there is no light, it's going to take place, and that is something that we'll come back to in the next part of our discussion. Okay. Now, one more thing that I can do here is that in this equation, NL is a variable, Nm is also a variable, and it's not so easy to handle both. But then the good thing is NL is simply N minus Nm, isn't it? Right? Where N is the total number of molecules. So I can write this as N minus Nm. Okay? Let me collect the terms in Nm on the right hand side. I can write Nm multiplied by, oh, everything is minus. So minus B rho nu minus 2B rho nu Nm, I don't have to write Nm here, plus A, this whole thing can go into brackets, inside brackets, Nm, and what is the non-Nm term? B rho nu N, right? You know what to do, dNm divided by B rho nu N minus 2B rho nu plus A Nm is equal to, I can write dt. One kahan se aaya? Now, then of course I'll integrate, right? I'll integrate the right hand side between 0 and t, and I'll integrate the left hand side also. But before I do so, let me write this dNm as d of this. So I can write this as d B rho nu n minus two b rho nu plus a nm What do I multiply outside? Numerator or denominator? Huh? Denominator minus 1 by 2b rho nu plus a. Is that right? Is that right? What are the limits? What are the limits of this function? At time t equal to 0, what is nm? 0. So second term vanishes, first term persists, right? So the lower limit is b rho nu n and the upper limit is the whole thing. Okay, so far so good, not very difficult, I hope. Then I can write, yes sir, because we are assuming that sorry, no, but we don't forget where we had started from. Actually, this nm is difference in population. We are saying that when you start with, the system is completely defined by capital psi L, right? That means nm has to be equal to 0, isn't it? Okay, so what do I get here? I can erase all this, isn't it? Right hand side is very easy. What is the right hand side? I can take this up to there. Minus 2b rho nu plus a multiplied by t. That is very easy. Even left hand side is easy. ln b rho nu n minus 2b rho nu plus a nm divided by b rho nu n. Is that right? So ln, you know very well what to do. Get rid of ln, right? This is e to the power minus this thing. Okay. Now what do I get? I get, maybe I'll write like this, 1 minus 2b rho nu plus a divided by 2b rho nu. We can of course simplify this further, multiplied by nm is equal to e to the power minus 2b rho nu plus a into t. So finally I get is equal to, I can take this on that side, 1 minus e to the power minus 2b rho nu plus a into t, and on this side I have, where is NL? Where is N? I forgot to write N here, isn't it? On this side I have, let me write like this. That is taken care of anyway. So Nm divided by N will be equal to what? 1 by 1 plus A by 2b rho nu. 2b rho nu divided by A plus 2b rho nu. Is that right? Now I'll divide. I get 1 here. I get 1 here. and this is, that is also not required. This is enough actually. Okay, right. Now, this is the expression I get. Now let us see. What is the left hand side? So what is n? Don't forget. What is n? Right. So Nm by n is the fraction of molecules in the higher level. What is the condition for population inversion? This fraction should be greater than half. Okay. What is this value when t is equal to 0? T equal to 0, it is 0, right? So if I want to plot Nm divided by n against t, I start with 0. What is the value if t equal to infinity? Right, right. So the curve is going to be something like this. Isn't that so? There will be a limiting value. So now we come to this question, what is this limiting value? Is that limiting value equal to 1? Can it be equal to 1? Can it be equal to 1? Because then you are left with only this coefficient, right? Okay, can it be half? When will it be half? Only when a equal to 0, right? So that is the limiting value, we can think that when, so first of all, so what you are asking, it can never be 1. It can be half if a equal to 0. Now let me ask you the question, can a be equal to 0 if b is not equal to 0? Remember what we had discussed in one of the previous classes? A is some constant multiplied by b, right? So if b is not equal to 0, then a is not equal to 0 either. So actually, a can be much smaller than 0 as we have discussed. What does it depend upon? Ratio of a and b. What does it depend upon? Isn't it something like nu cube by c cube, something like that? Right? So when what happens is when nu becomes large, then a gets a chance, a becomes larger. When nu is small, then a becomes smaller. But whatever it is, it can never be 0. So this limiting value is going to be half, and you will never get population inversion in a two-level system. That is a very important take-home message, that for a two-level system, you can never achieve population inversion. Therefore, you can never get stimulated emission for a two-level system, and therefore, you can never hope to make a laser if a system has only two levels. Did I come to, did I throw all this at you a little too quickly? Okay, then let's say it once again. You agree with me that the limiting value is half, right? Nm by n, limiting value is half. And when is this limiting value achieved? Only at t equal to infinity. But then t equal to infinity, if you want to go there, Schussnacher will be very unhappy. Right? Because the perturbation theory will not work anymore. So you can never go there. You have to restrict yourself somewhere here. So for a two-level system, Nm by Nl, Nm by n is always less than half, which means no population inversion. And if you remember, what was the essential condition to get net stimulated emission? Population inversion, right? So we see that since there can be no population inversion in a two-level system, it implies that you cannot make a laser out of this two-level system. You cannot get net gain from a two-level system. But of course, lasers are there, right? We use lasers in our classrooms as well, right? Everybody has seen a laser show somewhere or the other. Lasers are there everywhere. You have laser printers in labs and homes. So how does one make lasers? Of course, you cannot make lasers out of two-level system. What you need is you need to add more levels. Next day, we are going to discuss how you can get, I'm not done yet today, I will discuss something else. But next day, we are going to discuss how you can actually get net stimulated emission and therefore how you can actually make lasers out of 3-level and 4-level systems. And we also discuss what is the difference between these 3-level and 4-level systems. Once we are done with that, we'll take a brief walkthrough of laser spectroscopy. That is the reason why we are doing it. Otherwise, laser is optics, therefore physics, right? But the reason why we study lasers in this course is that we also want to tell you a little bit, not too much, about laser spectroscopy. Okay? So that is what we'll take up in the next class. The take-home message for today so far is that you cannot make lasers out of two-level system because it is impossible to have population inversion and therefore impossible to have net gain if your system has only two levels. When we talk about lasers, what we mean is that we must have a net gain, right? We use the word gain, right? We must have amplification. That is the point. You can observe some stimulated emission, of course, but you cannot make a laser out of it. To conclude this discussion of two-level system, let us do something. To start this discussion, what we had done is we had turned the light on, right? We said there is no perturbation, the system is in psi L. You turn on the perturbation, turn on light, and the states start mixing. You get a sum of these two wave functions. Now to conclude the discussion, let us turn the light off. Okay? Now let us say there is no light. What happens then? Of course, at the instant when I switch the perturbation off, there is some excited state population Nm. Alright? So what happens? The moment I switch the perturbation off, does all this population deplete? Do all molecules come down to ground state in an instant? Not really. Because don't forget, what are the processes that are cut off? We talked about three processes, right? Stimulated absorption, stimulated emission, spontaneous emission. First two are associated with B, Einstein B. The last one is associated with Einstein A coefficient. First two, of course, are gone, right? The moment you switch the light off. They are induced processes. What about the third one? It is spontaneous, right? That will still be operative. So, the rate of decay of excited state population, if I write dNm dt, that should be in that case minus A into Nm. Do we agree? All we are doing is we have taken the same Einstein treatment, but now since the light is off, we have removed the first two terms. We are working only with the third term. Are we clear? Very simple equation. If I solve it, what will I get? But Nm, I'll just write T explicitly now, at T is equal to, yeah, Nm at time 0. Don't forget, in this case, time 0 is the instant at which I have switched off the light. So there is some population in the excited state. I call that population Nm at time 0, multiplied by what? E to the power minus A t. So what we expect is an exponential decay. Same treatment as what you have done in your chemical kinetics class in class 11 or class 12. Okay? We expect an exponential decay of the population. Okay? It is conventional to write this expression not as in the terms of A, but in terms of what is called lifetime. In this case, I will call it tau r, where tau r is equal to 1 by A. It is called radiative lifetime. So the process you have here essentially is relaxation. So far so good? Agreed? Now, by the time we end this discussion, once again what we will do is, we will build another bridge between experiment and theory. If you remember, in one of the earlier discussions we had recently, we said that you can express A and B in terms of that stylized A, right? What was stylized A? It was an absorption coefficient. You can easily express it in terms of epsilon, which is an experimentally measurable quantity. We will conclude with something similar today as well. Okay, this is lifetime. All right. Now let me ask you a question. Is everything emissive? Is everything in the world emissive? Right? See, you're wearing shirts, they are colored usually. Even if they are white, they are actually colored. It's just that all colors are present. But do they actually give out light? I mean, if I turn off the light, for some time, are you going to see a glow? Not really, not usually, unless your shirt has some fluorescent pigment in it. Okay? So, actually most of the colored substances that we see are non-emissive. Why are they non-emissive? Is it possible that A is equal to 0 for them? No. You understand the point I am trying to make? For anything and everything, A can never be equal to 0. You told me 15 minutes ago. If there is a color, that means there is a transition. That means B is non-zero. Okay? If B is non-zero, A can be non-zero, A cannot be 0 either. Why is it then that we don't see emission from anything and everything? The reason is, we have not considered something so far. You have two levels. We have said we have absorption and we have emission. But I think most of you know that it is also possible, and in most cases that is the predominant thing that happens, is that you can have what is called a non-radiative relaxation. The point is, there are several pathways available for the molecule to come down to the relaxed ground state without having to give out a photon. Okay, I'll take a very, very simple example. I'll just write some arbitrary groups A, B, C, D. This is a CC double bond. Okay, is it possible to for a cis alkene with CC double bond to become transalkene? No, right? Cis trans isomerization is not possible. Why not? Because it's a double bond, right? Pi bond is there. But suppose I now do a what is called a pi star excitation or transition. Then what happens? Now, as long as it is in the excited state, pi star transition has taken place, right? So you have one electron in pi orbital, one electron in pi star orbital. What is pi bond order in the excited state? 0. That means in the excited state, this has become a single bond. Now it can rotate. The moment it rotates, that itself is a non-radiative process that happens. Photoisomerization. In fact, photoisomerization is taking place within all of us right now in this room, because we are seeing each other, right? Photoisomerization is an important part of vision process, among others. So there are several non-radiative channels that are usually available for relaxation of excited states for the system to come down to ground state. So our discussion is really not complete here. We have defined radiative lifetime, fine. But if we really want the whole picture, then I should write not just A, but some other term. I choose to write A plus KNR. N for non, R for radiative. KNR is the non-radiative rate constant. We'll just need 2-3 more minutes. Please bear with me. So if I do this, this expression just gets modified in this way. Now I don't call it tau r, I call it tau. So tau is 1 by A plus KNR. This is called the excited state lifetime. So lifetime of the excited state is merely the reciprocal of the overall rate constant for de-excitation of the state. Any question? Yeah? Okay. Tau equal to 1 by A plus KNR. Do we have any question here? Have you all understood? Can I go ahead? Great. I leave it to you to figure out. So this is homework. You can write down. Prove that this tau, we call it lifetime, right? Why do we call it lifetime? Something, it's not half-life. If you simply put t equal to tau, what do you get? See, nmt, nm at time t divided by nm at time 0 is equal to e to the power minus t by tau. What happens if you put t equal to tau? Right hand side becomes 1 by e. What is 1 by e? Approximately 1/3. It won't be 0.69, 0.33. Yeah, approximately 1/3. So it is not half-life period. So this is, you can say very roughly, the time for the excited state population to decay to about 1/3 of its initial value. But more importantly, it is the average time spent by a molecule in the excited state. So I request you to work it out by yourself. It's there in many books. Lakovich topics in fluorescence spectroscopy would be a good reference among others. You can also look up photochemistry books by Rohatgi Mukherjee or Rohatgi Mukherjee. That's one name, Rohatgi minus Mukherjee, not minus, hyphen. It was Rohatgi plus Mukherjee, that's why it became Rohatgi Mukherjee, not minus. Rohatgi Mukherjee's book is good, or you could see Turo's photochemistry book, Nicholas Turo, photochemistry. Okay, all right. It is the average time spent in the excited state by a molecule. You can work that out yourself. But what we end our discussion today is this. Remember, we had talked about steady state some time ago, right? What is the meaning of steady state? Rate of excitation is equal to rate of, I can call it de-excitation. So in steady state, what you can write is rate of excitation is your A plus KNR. Will you agree with me? Rate of excitation is A plus KNR because that is your, well, multiplied by Nm. Okay? A plus KNR multiplied by Nm, excited state population, is the rate of de-excitation of the excited state, right? And here I have considered radiative as well as non-radiative, everything, channel, all channels. So this is rate of de-excitation. At steady state, you can equate it to rate of excitation as well. Okay, now I bring you back to something familiar, something we had written earlier. What is emission quantum mean? IEM by IABS. Can I not call this rate of emission divided by rate of absorption? Right? So rate of absorption I know already. It is A plus KNR or tau, you can say. What is this IEM? Not emission quantum yield. It is A into Nm. Right? Rate of emission For rate of emission, you have to only look at the emissive channel. You have to neglect the non-emissive channel. So ANM divided by A plus KNR NM. NM and NM cancel. What are you left with? You are left with A multiplied by tau. Okay? Phi EM is equal to A multiplied by tau. What is 1 minus phi EM? Can you work that out for me from here? 1 minus phi EM. Just do the algebra here. 1 minus A divided by A plus KNR. What are you left with? KNR by A plus KNR, and we know that 1 by A plus KNR is tau. So it is KNR multiplied by tau. Now see, you know how to determine quantum yield, emission quantum yield. You did that last evening. How do you measure lifetime? We'll discuss it very briefly when we talk about laser spectroscopy. But just believe me for now that it can be done experimentally. So you do these two experiments, steady state emission experiment and you measure lifetime experimentally. What you can find out is you can find out the rate constant for the non-radiative process that depopulates the excited state. So if you are talking about photoisomerization, for example, I should be able to find out what is the rate constant for this photoisomerization process simply by doing a steady state experiment and measurement of lifetime. Last point, absolutely last point is, how do you find A? You don't have to do it experimentally, isn't it? Remember, A is related to B and that is related to epsilon, right? So if you have experimentally, suppose you have done an absorption experiment. From there you can find out what is epsilon. From epsilon you can find out what is stylized A. From there you can determine A. Okay? So once again we finish in a situation where you have a nice correlation between experimental and theoretical quantities. You do an experiment, you can find out the value of this theoretical quantity. You determine the value of the quantity theoretically, you can try and predict what your experimental results are going to be. Okay? We stop here today. Next day we start talking a little more about lasers and laser spectroscopy.